Yeah, Docas, please.
Hi, good afternoon, everyone. So today I'll be presenting this paper titled "You Can't Debug This: Detecting JavaScript Anti-Debugging Techniques in a While." The authors of this paper are a PhD student and professor from a university in Germany, and research interests are in web application security with a focus on client-side attacks, meaning JavaScript HTML. So for this particular study, I'll be presenting the sections in the same order they're written. There are two major parts to this study. The first one is about basic anti-debugging techniques, and then there's a second part, which is a follow-up study on more sophisticated attacks. I'll go through them in detail later.
So here I'll just have a minor suggestion. So debugging is basically to extract information from the code. And I think the most successful anti-debugging technique need to hide the most informative variables or information. So basically, debugging is basically analyzing the runtime information, right? So what we care most is about which information and what runtime information need to hide, right? So let's keep going on to see how the authors address the problem. Yeah, Docas, please. Oh, by the way, Docas, have you prepared the 3 questions for the audience to?
Yes, I have questions later.
That's great. Yeah, in order to improve the interaction and discussions, and Docas will giving 3 questions for the audience. And of course, I'm the audience, but I think I'm not supposed to answer. But then Docas will randomly point one author to answer the questions. Yeah. So please focus and prepare the questions.
So the background behind this research is JavaScript code in the web. So whenever anyone visits a website, they need to execute JavaScript code locally, and this code is executed in the browser. But browsers are complex, so it's possible for these browsers to have bugs, which means that in order to maintain the security of the web, it's very important for researchers and other professionals to be able to detect and to analyze malware in JavaScript. The analyzing JavaScript from a static approach, meaning just looking at the code, is not very feasible because it's possible to obfuscate the code, and it's also possible to generate new code during runtime, which means that in order to effectively detect malware, researchers often rely on dynamic analysis or a combination of static and dynamic analysis. And this in turn leads to attackers becoming more advanced. So they create evasive malware, which is able to detect when it's being analyzed dynamically. So to detect when the researcher is looking at the behavior of the program and then to change the behavior accordingly. So there has been research on all of these aspects, but one area of research that's often overlooked is the manual analysis of websites using a normal browser. So these are some examples of anti-debugging techniques that were done before this work. So for example, there's a malicious script that mines cryptocurrency until somebody opens the developer tools at the side of the browser. Then once developer tools are open, it stops. And similarly, malicious script in online stores, it records credit card information and then sends it to the attacker. But if somebody opens developer tools, which means they're trying to analyze the website, the script will stop sending data, and then it will never again activate scheming for the user again, which means that if I'm a researcher.
This sounds interesting, but how the JavaScript code can detect this event?
Yep, so this is how it detects it is the area of research for this particular paper. So the summary of this paper is there are 9, and it proposes 9 anti-debugging techniques using JavaScript. The first study is a large-scale study, which looks at 1 million most popular websites and looks at this 6 basic techniques. And then the second study is a more targeted study, which takes the top 2,000 websites from the first study, and then it investigates more advanced techniques that are more difficult to detect. So now going into a little bit more background. So we mentioned developer tools just now, and this is what analysts will use to look at the code that's running in the browser and to see what's happening. So there's Elements tab, which gives you the DOM tree for HTML, and then the Sources tab, which allows you to view all of the sources, as well as set breakpoints. So set breakpoints and view the call set and scope of any
By the way,
variables.
so may I have a small investigation? How many of us have tried to play with the browser and debugging the online programs before? To set a set point in the Chrome and debugging the JavaScript. How many of us have done that before? Yeah, there's so I assume that Yuchen, have you tried it before? Hello, Yuchen.
Oh, sorry. Yeah, I have, but I don't usually use the breakpoint in the dev tool itself.
Okay, so you never
Yes.
try to break points on the code. Okay.
Yeah, it's usually from the dev server and the local
How about you debugging the
development
front end?
environment.
How about debugging the front end, or if you want to invest in the website? And by the way, Yijie, have you tried before?
No, not really.
Okay, so maybe you can have a try. You just open an arbitrary website, and you can observe their JavaScript, and then you set a breakpoint. You can understand. You can execute the JavaScript line by line and step by step, and observe what it looks like. Okay, let's keep going on.
Yeah, okay, then the console tab allows you to execute arbitrary JavaScript, and then the network tab gives a full inspection of all network traffic. So any requests that the browser makes to any web server, for example. Okay, so this one is just a simple question. So from the 4 tabs that we mentioned earlier, which one should I use if I want to find the value of a specific variable? Is it yeah.
Yeah, so anyone want to have volunteer on this question? And then volunteer there. If not, Docas, you can just point out. Hey, Junbo, yeah, Junbo, you want to have a try?
It's just elements don't true.
Okay, actually, I think I was a little not specific enough. So I meant actually, what if I'm trying to analyze the value of a JavaScript variable at some point in the script?
Yeah, so the JavaScript, we're talking about the JavaScript variable. And I, by the way, the DOM tree where there's any variables in DOM tree, I don't know.
DOM tree, not so much. The DOM tree mostly refers to the HTML.
Yeah.
But
Yeah.
not this one. Yeah.
Yeah, any volunteer have a second try?
Is it B, like where you can set up breakpoints?
Actually, it's B and C, because in the console tab, you can also.
So it's not a single choice, it's multiple choice.
Yep.
Okay.
Yeah. So in the console tab, you can also set a breakpoint and then to analyze the scope, analyze code.
Yeah.
Okay.
Yeah. So,
So
let me rephrase it here. So if we want to debugging JavaScript, we can either set a breakpoint on certain line and observe the values of some variable, or we can type in the console and to retrieve the runtime variable. Maybe you can in the console, maybe you can also have providing typing some expressions to evaluate the value of some expressions. Okay, let's keep going on.
Okay, so this is part of the motivating factor for this work, and that is that any JavaScript code that is written for the web needs to be analyzed using a browser. So you can't. It's not so easy to just run it in, for example, Node.js outside of the browser. So, for example, the JavaScript code tends to expect objects that are not part of JavaScript itself, but they are part of the browser. For example, the document and location, and the scripts often load additional code on the fly. So, for example, a JavaScript script might generate code for an iframe to insert it into the HTML for the page. And so when you're executing the JavaScript, it needs to make a web request to fetch the additional code and then insert it into the page. So as a result of that, there are causality trees in the script inclusions. So only a real browser can be used to accurately inspect or to analyze the JavaScript code. So
is there an examples or the models here? So the basic idea is that some JavaScripts are I'm going through the first point. So you mean that the JavaScripts are not part of the language? So can we more specifically that the JavaScripts are not part of the language specification? And what do you mean by the language specification there?
So
And
specifically, JavaScript that's written for a browser, it uses certain objects. For example, it can access properties of the browser window, and this is part of the standard. This is part of the standard for a browser, but it's not part of the standard for JavaScript itself. Which means that if you want to execute it in, let's say, a JavaScript sandbox, you would basically have to create a whole entire browser in order to be able to execute the JavaScript code.
yes, yeah, assuming that, so the first point that some JavaScripts have to be run inside the browser. So is that point? Or I still miss the point.
Yeah, the point is that it needs to be run inside the browser.
Okay. All right. Okay. So the first point that the JavaScript have to be run inside the browser. So the second point means that JavaScript, even when the loadings, they will actually keep loading some code elsewhere, so that we need to analyze the code on runtime, right? Okay. Yeah, I think that the second point is very interesting, and there's especially the correlated tree. The correlated trees here. So when we're loading the code will keep loading new code, and actually the code per se is maybe safe, but the loading code is malicious. So that means that if we may not easily to identify the code just from a static perspective, we have to run it and confirm its intention, right? Okay.
Okay. So the threat model that this research paper is addressing is when a security analyst manually visits a website using a real browser in order to analyze and interact with the browser's code. For example, if the analyst is trying to create an automated tool to analyze the website's code dynamically, they'll probably first want to do some manual analysis to confirm some of the hypotheses. So when they're doing this, they often use the integrated developer tools, and the analyst might want to browse the source code and set breakpoints, etc. However, on the website, which is set up by a malicious actor, it does not want to be analyzed. So it contains evasive measures in order to detect when the analyst is looking at the code and to hinder the analyst's attempts to inspect the code. Okay, so just a bit of context. We mentioned, Dr. Lin mentioned obfuscation just now, but obfuscation is a little bit out of scope for this paper. What they're focusing on is dynamic analysis, which they're calling anti-debugging techniques. So for example, detecting whether a debugger is present or not. Right, so now going into the actual techniques. The first section involves 6 basic anti-debugging techniques. And these techniques have 3 goals. The first one is to impede analysis, to prevent the analyst from being able to do any analysis work. The second one is to alter the results, which means that the program behaves differently when it's being analyzed versus when it's not. The last one is to detect whether alter its results is to give a different result when the analyst is, for example, trying to lock the program. And then the last one is to detect whether an analyst is actually carrying out, has the developer tools open. The authors also created a test bed with example implementations, which you can have a look at if you're interested. Okay, so the first technique that's presented is a very simplistic one, which is to prevent any analyst from opening developer tools using a keyboard shortcut. So basically, it adds an event listener, and if it is a keyboard shortcut to open developer tools, then it just prevents it. But this is quite easily bypassed by you just opening developer tools without using a shortcut. The second one is to trigger a breakpoint. So the debugger statement is a statement in the JavaScript code that has the same effect as manually setting a breakpoint. So what this does is that this code repeatedly triggers a breakpoint. So it runs debug and then it sets a timeout so that this will be run again 1 millisecond later. And what this means is that if I'm an analyst and I have developer tools open and I'm actually trying to step through the code, I won't be able to because it just keeps going into this breakpoints. This one is also not very difficult to bypass because there's an option to disable breakpoints. So somebody can just disable this breakpoint. And in advanced cases where the malicious script generates code that contains the breakpoints on the fly, you can also run an anti-debugger script that removes all debugger statements completely.
By the way, so giving the code looks like this, isn't it is a kind of obfuscation? Or you can see, so by right here it is an infinite loop here, right?
Yeah.
It is infinite loop. So I'm not sure. So this part of code, if there is infinite loop, it will just consuming the computing resources in the browser, but not for nothing, right? So even this kind of the code obfuscation, and by the way, so this anti-debugger, so there are scripts just to detect where there's infinite loop there and just delete them. Is that the anti-debugger script do?
Yeah.
Right. So okay. So in this case, those kind of anti-debugger, the anti-debugger scripts is kind of the obfuscation. So once we have the code layers, we'll just go through all the code and find the irrelevant code or the code that actually provide nonsense and just delete them. Am I right? Or
I think the objective, it's not so much to deobfuscate the code, but it's specifically to handle this form of malware.
Yeah, so the point is that so there's two choices or two possibilities. The first one is that this piece of code is really a debugging code, right? If it is debugging code, that, for example, if when I write a program, I'll still leave a few debugging code for me to observe some runtime information. Maybe sometimes debugger is not convenient, and the code may be helpful. And then the other way is that this debug code is actually used as the anti-debugging purpose. For example, if we set breakpoint there, and it will actually loop and keep coming back the loop. So my question here is for this piece of the code, it is a normal debugging code, or it actually deliberately setting for anti-debugging, or this is just kind of malicious code.
It's set specifically for anti-debugging.
Yeah, so it is malicious, right?
Yeah.
So it's malicious. In this case, then if it is malicious, we yeah, maybe I don't know, maybe this part of code, if I'm a programmer, when I understand this is nonsense or this is part of code I'm not interested, I can just remove the breakpoint and looking somewhere else.
Yeah.
Okay, let's keep going on.
Okay. The third technique, it's also a very simple one, which is it also uses an infinite loop to make the console unusable by constantly clearing the console. So if I'm trying to run code using the console, then it will just keep disappearing. However, it can be circumvented by preserving the log, so the history of commands in developer tools, or you can analysts can also disable the clear function by redefining it to an empty function.
By the way, I'm not expert in JavaScript. So that means if you run a JavaScript in the browser, you can close the console in the browser. Am I right?
This function, it removes the previous statements, but it doesn't close the console.
Oh yeah, so just remove it. Okay. Okay, I see. You keep going on.
Okay. So this next technique aims to not just stop an analyst from running their code, but to alter the analysis. So what some malware authors might do is to monkey patch the built-in functions. So for example, in this case, they changed the window alert function in order to do something when an analyst tries to use alert to debug the JavaScript code. So when that happens, then they can change the results. It can change the results when the analyst tries to debug. Okay, so for example, I think the right side.
Let's see.
Yeah.
Please, yeah.
Yeah. So okay, for the left side, what it does is to wrap the window alert is a function that creates a pop-up when it's called. So what this does is it logs the results. It logs the contents of whatever is done in the alert before it applies window alert to the original arguments. So for example, if I'm an analyst and I'm trying to let's say I try to create a pop-up that contains some data, the attacker's backend will receive a stack trace as well as all the code that I tried to pop up in my browser. So I will still see it, but the backend, but the attacker's backend will also see it, and they can see what I'm trying to do.
So as long as the users cannot see these function rewritten or the rewritten functions of the Windows alert, it will get nothing when on the pop-up window, right?
It's possible to redefine it so that the user doesn't see anything. But in this case, the user will still see something. It's just that the attacker will also see it.
So this is the attacker is just to do the log, right? So the arguments, yeah. So the point is that when we have these functions of the very redefined Windows alert functions, the attacker has the flexibility to change anything change the content of the pop-up messaging, right?
Yeah.
Yeah. So in this code, of course, it just log the informations and redirect the informations on the windows. But sometimes else, it can just output nothing, right?
That's one example of that's on the right-hand side. So they wrap the original console log function. So if the argument is, this is a simple example. So if the argument is a specific piece of code, then you can change the argument so that the analyst will see something different in the actual log.
Okay, let's keep going.
Okay, the next two functions don't change anything that the user sees. They don't change it directly, but the main objective is to detect whether developer tools is open. So this with difference technique detects whether anything is open on the sidebar or at the bottom of the window. So it records the outer width of the window as well as the inner width. And then if there's a difference, means that for example, there's like something open on the right side or at the bottom. This is a very simplistic tool. It doesn't work if I open DevTools in a different window. And if I have another kind of sidebar, for example, some browser extension inside, it might also report a false positive. However, for most cases, it is sufficient to detect whether it's open, and then it can change the code. Okay. Then the last technique is the most advanced one. This is not just one technique, but it's a collection of techniques. As the browsers have evolved, the technique has also changed over the years, but some variation of it is still working at the time of writing. So in this example, what the malicious code would do is to create an object with a custom toString function and then log it, so that once the developer tools are opened, it will try to log this object, and then the toString function will be called. Another variation that was listed is to create a function that monitors its ID property, because once developer tools is open, developer tools will try to access the IDs of every object in the code, and then that function will be called. This particular technique is difficult to overcome because there's no real countermeasure unless you remove all logging functions of the console object. So to redefine log to something else, but this is also invasive. And if the malicious script is advanced enough, it can detect that I'm trying to redefine console log.
So let me repeat here. I hope that I understand your point. So we have a function called logme, right? And here we redefine the two string functions. And so here, maybe we can re-emphasize this, how the code detects the develop tools that opens. And I understand that when the developer tool is open, you're trying to monitor the ID properties. And yes, apart from this, is there any triggers or any detection measurement?
Okay, so this function is one possible way. The other approach that over here is that when developer tools is open, then it will try to log it to the console. But if developer tools is not open, then it doesn't run this line. So this isn't called.
Okay, I see.
So
okay, so let me wait. We will go back to previous slide. And the point is that when the developer tool opens, it will try to log every functions, right? It's going to log every function, defining the scripts. Is that really true? So we have JavaScript, and why the developer tools will try to log everything, log every functions?
okay, in this one, developer tools will not log every function, but because there's a console log over here, so because of that, then it will try to use the toString function to create an output for this logme.
And so will this be more specific on how the code can detect the developer tool is open? So when a developer tool opens, what code will be triggered? Can you be more specific on that?
I see. So if developer tools is not open, then this toString function will not be called.
Will not what?
Then the toString function is not called.
Will not call, okay.
Yeah, but when developer tools is open, then it will run this code and it will try to log this anonymous function.
And why the tool will run this code?
Because developer tools will try, it will try to, because in order to create in JavaScript to create the output for an object, it will try to look for the toString function of that object. So when
so that means when the developer tool is open, this code is not functioning. So this code may not function. But when something using the console in the tool to print out something, and this part of code will trigger. And when part of code triggered, and it will just for example, usually we want to invoke toString function, right? So the basic idea is that we want to redefine the toString function. And if it's recalled, if the toString function is called, and we know that I'm triggered. If I'm triggered, I'm just to remove some of the code in the JavaScript. Is that the technique? Is that the technique? Yeah. So yeah, I think that is a clever one. So not like Java code, JavaScript is very flexible. And it can, as long as something in the Java, as long as there's something in the browser or in the document, it can change everything. So one of the ideas is that we just redefine the toString functions. When someone is called toString functions, and we just remove everything. So yeah, that is kind of clever. And let me think about it. And what is potential countermeasure for this technique? Or we just go through, and I think you can define a few heuristics to address this problem. For example, we only see that whether toString function is a pure function. Pure function is that it will not modify anything in the code. It will just print something, right? So that is the potential toString responsibilities. If the toString functions modify the code, it means that toString function is not that static. So it may raise something special there. I don't know, maybe that is controversial. Let's keep going on.
Okay. So the authors categorize the techniques based on 4 criteria. The first one is how effective it is, so how likely it is to be activated. So for example, the shortcut may not be activated if I don't try to use shortcut to open developer tools, but logget will be open as long as the console is open. Second one is how stealthy it is, whether it tries to remain unnoticed. For example, console clearing is not stealthy at all because as an analyst, I looked at it, I can see immediately. And then how versatile, whether it can be used to achieve many different outcomes, and how resilient it is. So whether it's easy to bypass or not. This one, another easy question. So from attacker's perspective, which technique is the best to use? Open to the floor.
Yeah, so the question is which technique there is the best for an attacker to use in terms of different property or different feature there. And anyone would like to have a try. If there's no volunteers, Docas, do they have a point one to have a try?
Okay. Xianghui?
Hello. Yeah, I guess from my perspective, it should be logget. Yeah.
Yep.
Yeah.
Yeah, okay. Yeah, it's an easy question. So logget fulfills 3.5 out of all 4 criteria. The only thing is that it might be noticed because it actually does log something to the console. Okay, now going on to the actual study. So in order to detect these 6 techniques, we mentioned earlier that the JavaScript needs to be analyzed in the browser. So the researchers used a Chromium browser controlled by Node.js, and they use this thing called the DevTools protocol, which is an API that allows you to control certain properties. Then they detected the presence of these techniques and how often they occur. Specifically, they only count occurrence in the main frame of the loaded page and not any iframes and not any additional frames that are added. And they only count the techniques once per site. So for example, if every page uses a console clear, it only counts once. For each of the techniques, I'll go through this quite briefly, but they make use of the DevTools API in order to detect them. So for example, shortcut, it collects all event listeners, and then it passes a keyboard or mouse event that imitates the shortcut to the listener, and then it checks whether default prevented is set or not. Then for console clear, it registers a callback with the runtime console API called hook to observe how often console clear is called. So every time it's called, this callback will be called, and then I can check how many times console clear is called. Yeah, I'll skip some of these. Then for mod build, it's a bit more interesting. So the analysts inject JavaScript code that runs before any of the website's code, and then they monitor all objects of interest, for example, string. And then since they are monitoring all of the properties, if the website's code tries to override any of these objects, then the backend this website gets flagged out for modifying built-in functions.
And this website will be, but anyway, so what if some denied website is still trying to rewrite an objects?
Yeah, so they will still get, so this method, it may catch a number of false positives, and then the researchers will have some other heuristics later on to detect how likely it is that this is, how confident are they that this technique is being used maliciously or not.
Okay. By the way, Xianghui, you don't see that this design style is very similar to our empirical studies last week. So the idea is, but actually they're working in a very different context. So the context is that when we are using Git, we have a lot of the commit history, right? Sometimes we delete some things, we add some things, we refactoring some things. We eventually we're writing the code. So basically we want to identify what kind of commits, what kind of code commits are refactoring, and what kind of commits are feature enhancement or bug fixing. So we want to analyzing those, we want to attach the label for each commit, but there is also a rough estimation instead of 100%. It's not instead of 100% accurate detection. Yeah, maybe we can talk more about this later. Let's keep going on.
Okay. Yep. Then for logget, they use the console API to flag whether okay. So in the example earlier I showed, when we're using, sorry, where is it? in this example, it blocks the function together with a format string. So in order to detect this, they flag out any time a format string is used with a function that has a custom to string method, or when an object has an ID property that is a function instead of value. Okay. And the experiment setup, they visited the 1 million most popular websites according to a Tranquil list. Then it waited for up to 30 seconds. Then after loading it, waited for another 3 seconds for pending network requests. Then they waited another 5 seconds on each loaded page so that some techniques will have enough time to trigger multiple times. And then they, after this, they also selected 3 random links from the main page to an internal subpage to visit. So for example, if I'm on the website, there's a home page, there's a about page, there's maybe like a sign in or login. So then they will select 3 out of these additional links to go and visit as well. And the question, and this is my last question for the presentation, which is why do they want to visit internal subpage? Why not just look at the main page of a website?
Yeah, and a volunteer here. Yeah, so anyone want to have tried? So here, so let me repeat the questions. When we are crawling the website, and we definitely, or we have some routine there. For example, we need to fully load the web page here. And additionally, we, according to our Docas, we will select, the authors will select 3 random links, but it is an internal subpage to visit. And what is the reason for us we need to choose 3 internal subpages instead of external hyperlinks here? So anyone want to have a try?
Just a guess, but is it because if we chose external hyperlinks, it could muddle the data, so like you wouldn't be able to track, you'll be able to collect like which techniques are used in which website, because in some cases you exit the website through external hyperlink instead of internal subpage.
Yep. Actually, the question was why do I need to visit an internal sublink instead of just looking at the main page?
Okay.
Yeah. Instead of sorry, the main page. Okay, keep going on. Yeah.
Well, my guess would be that there might be some, you want to watch out for some techniques that take some time for you, or some techniques might only activate if they determine that you're actually like browsing the page, not just like scrolling the main page and running away. That's
Okay.
my best guess.
Okay, that's a good guess. The reason that was cited in the research paper is that one common evasive technique that malicious authors will use is to avoid running malicious code on the front page. So if I just do a cursory glance of all the top 1 million websites and I don't go into subpages, then I might not run into the malicious code. Okay.
No, wait. Let me think about the reason. So the reason is that they want to cryptojacking.
This is
this is an observation for the cryptojacking attack, right? So it means that the cryptojacking will not run it on the main page. It will just run on the sub page. And my question is why they don't run the main page. They have to run the sub page. Think about it. So when someone visiting this page, right? Maybe this web page is a gambling page, and why the attacker need to wait the victims to get the sub page and launch the attack? Why not launch the attack just on the main page?
If they run it on the main page, then most researchers will look at the main page when.
So it's just lockout is just a common invasive one, but how invasive it is. So when it is on the web main page, but in that case it may lose some chance. So any victims and if I'm the users but are not interested in the gambling. So in this case, I was not clicking to the sub page. Maybe I just leave the page there. I don't know. That is just a heuristic in people's mind. Let's keep going on.
Okay. Yeah. So some statistics of the 1 million websites, the 15 of them were lost because they couldn't be visited for various reasons. And then the total number of web pages visited was 2.8 million, on about 800,000 plus sites. Okay, so going to the results of the first part of the study, the number of websites that were flagged out for each technique is as follows. So the most common ones that were flagged out is with difference, which is to see whether the sidebar is open, or modifying built-ins. And as Dr. Lin rightly pointed out, these two might also be used for non-malicious reasons. So the authors also wanted to categorize, before that, the authors also wanted to see how often each of these techniques were triggered. For example, 1 or 2 console clears may not be malicious, but if the console is cleared 10 times in the course of 5 seconds, then that indicates that there's there might be some malicious activity involved. So how the confidence score was calculated was that the authors took the percentile of the number of times that the technique was triggered and calculated the percentile of it, then squared that value. So for example, if the console is cleared twice, if the console is cleared twice, it will be in the 60th percentile. So they take 0.6 and then they square it to be 0.36. So if it is in the top, range, then it will have a confidence score of 0.9 something. Then in addition to the confidence score, they also calculated a severity score. The reason for this is that you might have a website, a technique that is triggered less frequently, but is more severe. So in order to do that, they used a variation of the inverse document frequency from NLP, and it just it calculates a weight for each technique by looking at the number of sites with any technique over the total number of sites with the given technique. And then the final severity score is the sum of the confidence score times the severity times the weight over all techniques.
The point is that the technique will not be shared by all the websites, right? So the less the websites using these techniques, the more likely the techniques it is. The technique
malicious.
is malicious, right?
Yeah.
Might be. Okay.
It's a bit of a heuristic, but okay. So the results are as follows. The size and color show the number of simultaneous techniques on the website, and then the severity scores and number of techniques on each site is as follows. So most sites will contain either 2 or 3 techniques, and there are 4 sites that contain all 5 techniques. The authors also analyzed whether the techniques came from first-party or third-party code, and the results of this show that the different techniques have a very different picture. So for example, shortcut was mainly caused by first-party code, whereas with difference is mainly caused by third-party code. The authors rightly pointed out that even if a technique is triggered by third-party code, it could still be the first party's intention to interfere with the analysis by including the code. So for example, there's okay, never mind, I'll skip the example, not so important. Okay. In addition to that, the researchers also wanted to find out the correlation between the website rank and the prevalence of the techniques. So they noticed that the more popular websites had more techniques on them, and they also analyzed what proportion of the websites were caused by the same script. So for example, the most popular scripts for with difference contributed to about 80% of the occurrences. Okay. Then there's also some categorization of the websites. The most common one are, as expected, malware related and pornography. Okay. After this, they move on to do.
Yeah, I think those are interesting to know. But the very empirical study is what can we do based on the empirical results, right? Okay, let's keep going on. So is that what we are talking about now?
Sorry.
So I'm talking about, so we have empirical study. We know that there's some techniques to avoid being debugged. But the point is that what if we know these knowledges? What can we do? And basically,
Indicating.
yeah, and there's a lot of way to evade or to account or a lot of countermeasure to these. And then based on these phenomena, what can we do?
This paper doesn't quite go into that. The next part is about 3 other techniques.
Okay, the 3 other techniques here. Okay.
Yeah. So these 3 other techniques are timing based. So the main objective is based on the fact that certain operations become slower when developer tools are open. So the first one is to monitor an existing breakpoint. So in the malicious code, it contains a debugger statement, and then it compares the time before and after the debugger statement. So if the developer tools are not open, this will run faster. But once developer tools are open, then there will be a performance hit, and then once it crosses a certain threshold, then the attacker knows that developer tools are open. Okay. The second technique is it is similar, but it only detects if the analyst adds a new breakpoint to the document. So this it also compares the performance difference and checks whether it exceeds the threshold. But this has no effect if the developer tools are used without setting a breakpoint. Then the last one is called console spamming. There are a few variations of it. So previously, what was done, what they used to do was to create many text elements and then repeatedly add and remove them from the HTML DOM tree. And what that does is to slow it down. Is to slow it down significantly when developer tools open, because they will try to track what elements are removed and added. So currently what it does is to write a lot of output to the console and then to measure how long it takes. So yeah, this runs slower when developer tools open.
So here the point is that do that means the time is larger than the threshold and develop. But how the reason is that the console takes a lot of time. Is that the reason?
Yeah.
Or the rationale?
Yeah.
So it means that when we are debugging the code, the developers usually need the console to log and clear a lot of stuff, right? So in this case, so there's still a measurement, but I think the threshold may be different. If we set a breakpoint, the threshold can be 1 or 5 seconds, maybe 5 or 10 seconds, because the human need that amount of time to understand it. But if it's just console, it may be just a half seconds or a few milliseconds, and that is the threshold.
Yep.
Okay.
Okay. Once again, the authors categorize them based on the same 4 properties.
I have a question here. So why the authors does not put those evasive measurement into previous studies?
Yeah, the main reason for this is that these 3 techniques are difficult to do. It's more costly to measure them because there's a little bit of non-deterministic effects involved, which will be explained later. So the methodology for detecting these is a bit more expensive, which is why they focused it on the top 2,000 websites.
Okay.
Okay. So now going on to the targeted study of these last 3 techniques. The central idea is that if the anti-debugging techniques are present, the code execution will change based on whether developer tools are open or not. So they monitor the executed code twice, once with it open and once with it closed, and then they compare the 2 executions.
So
in order to,
I think a better way to run it 20 times, and a 10 times
yeah.
for the executed code with it open, and the 10 times with it closed, and we just calculate the statistic difference.
Yeah,
So
it's not actually twice, but at a high level, there are two sets of executions.
More like a comparative information. Yeah. But how the authors do?
Okay, so in order to execute the website's code in the exact same way, without influence from server-side logic or client-side randomness, there are a few methods. So firstly, the website is only loaded once, and then after that, all content is cached on a local proxy, so that when we are running the two sets of when we're running the comparison study, we always use the cache content. And then the second thing is to replace any randomness using a fixed pseudo random number generator, so that the results always be the same. And then for things like date and performance, they replace the built-in functions with a fixed timestamp. So that it always starts from the same time. The limitations of this is that the order of the events is not always deterministic due to parallelism. And in order to deal with this, they introduced a second concept called code convergence. So the idea is that the more times a website is replayed, the less likely it is to discover new execution paths due to the parallelism. And they measure, so what they do is to measure the code coverage, and then you stop executing once no new code is executed, which means that I've covered most of the existing paths already. So now what they do is to the summary of the methodology is first you replay any website in the same environment until you reach code convergence, meaning that they replay it until you find a baseline for how the website normally works. Then you inject analysis artifacts, for example, a debugger or breakpoints, and then you observe whether any new code is executed or any previously executed code is not executed. This third step of observation is not just done once, but if it's done multiple times, and if every time whenever debugger is present, this new code is always executed, or some previously executed code is always not executed when the debugger is present, then it's likely to be caused by an anti-debugging technique.
Okay, that is interesting.
Okay, so this is a similar setup as previously, including, but there's also artificial slowdown of a console in order to detect console spam, and they use this tool called Webpage Replay, which is used for debugging the Chromium browser. What it does is that it records and replays the loading of websites, and it also wraps common sources of randomness like math random and dates.
The point that is that possible that JavaScript to detect whether the WPR tool is running?
Sorry?
Is that a way for a JavaScript to detect whether it is running on WPR tool?
Yes, I believe so. And that's one of the limitations of the study.
Yeah, so, but how? And how the JavaScript now that it actually is record and replace?
I'm not sure about that.
Yeah, maybe the runtime, but I'm not sure. So the idea when it's running, so Xianghui and Yuchen are also working on a record and replay tool, but we're writing our own record and replay tool there. So usually their they're more like a plugin in the compiler or interpreter. For example, we modify the V8 compiler inside the browsers. So when the browser is interpreting the execution and compile the JavaScript code, it will run outside such a tool. I think the code itself is very hard to detect it. It is actually analyzing by the record replay tool. Okay, let's keep going on.
Okay. So they also added, the researchers also added one more extension to Webpage Replay, which is that it always answers with the same delay as the original server, just to reduce the sources of randomness. Okay, then the setup is that it records each website once, and then replays until there are 10 consecutive measurements without a change in code coverage, which is when the point we reach code convergence. And if if this condition is not satisfied after replaying the website 50 times, then they discard the site as being incompatible. Then after that, once they have this baseline, then they test each technique 5 times on the website and count if it caused a difference in at least 3 replays. Okay. So of the 2,000 websites that were tested, 33 out of them were not reachable in spite of the fact that this experiment was run immediately after the first one. So then after that, 6 of the sites did not converge. So they didn't satisfy the second condition over here. And then out of the remaining sites, 299 of them had behavior that was similar to one or more of the 3 techniques that were mentioned earlier. So this is about 12% of the total sites. So specifically, monitoring breakpoint was triggered in 138 of them. And yeah, okay, the stats are here.
By the way, how do they collect these 2,000 sites?
Oh, right. The 2,000 sites were the 2,000 websites that, sorry, give me a second. They were the 2,000 websites with the highest severity score according to the first study.
Okay, the severity score. Can you, sorry, I kind of forgot it. Will you please remind me, how do they calculate the severity score?
Okay, so the severity score is the frequency of the technique multiplied by the confidence that this, by the number of times that this technique.
The number of the sites with any technique. And those techniques are actually calculated based on the static analysis, right? So let's talk about
sorry,
so we have the technique.
These are also dynamic analysis.
You can call them dynamic analysis, but they do not need to run them repetitively, right?
Oh, okay.
You just implement it but you can think about it. So we have talking about it. Let's talk about the last 3 techniques as the temporal technique, right? And the previous 6 technique we can call this let's call it non-temporal technique. And why the how severe, but the severity, sorry, the pronounce supposed to, but how severe these techniques are evaluated based on the previous 6 techniques, and how can they be used as a website to detect the last 3 temporal techniques. Have I made myself clear? So you can see about it. So a user, it depends on what is the correlation. If a website using one technique, they can be served as. So the assumption that a website using one evasive technique is more likely to use other evasive techniques, right? This assumption. Otherwise, how they conclude there's such an influence and a correlation there. So that is my concern. Just like if we think about it, different label, for example, if someone like eat hamburgers, another one is that someone likes swimming, right? So it looks to me there are totally different features, unless that you have inference that someone likes hamburger is more likely to be a swimmer, unless we have the correlation there. Well, let's keep going on. Yeah.
The last thing that they did was to run the same second suite of tests on another sample of 100 randomly selected sites, and they only detected one site that has a timing related technique. So from this, that they inferred that the basic techniques are a good indicator for the presence of sophisticated techniques, and they also inferred that there's a low false positive rate of the methods of detection. So yeah.
Okay.
So discussion. Okay, as we discussed previously, these anti-debugging techniques can also be used for non-malicious purposes. So for example, Shopify has a script that runs to that detects whether, I believe, you're trying to reverse engineer the code, and then it prevents that. So these features, these techniques cannot be used as to classify a website as malicious, but they can be features for malware scanner. And similar to the previous research on obfuscation of JavaScript, which also does not necessarily imply malicious code. Then, as always, there are limitations to the study. The first one is completeness. not all anti-debugging techniques are included. The authors argue that it's complete in the sense that all techniques must meet at least one of the 3 goals. The authors also argue that another limitation is that false positives are possible and false negatives. For false positives, the authors argue that it's impossible to know the true intentions of any piece of code, but the fact that the website behaves differently under analysis, it means that the derived results cannot be regarded as conclusive. So if I'm a researcher and I know that, and I'm trying to manually analyze a website, this study will inform me that what I'm observing may not actually be the website's true behavior. There are also false negatives, and sites might escape the detector. So these results need to be regarded as the lower bound of anti-debugging techniques. So there might actually be more out there.
I think the first and the second are talking about the same stuff. Right?
Similar.
Yeah, they are the same stuff. Okay, let's keep going.
The authors also propose 2 areas for future work. So like Dr. Lee mentioned, the modifications of built-ins like date and math can be detected by self-inspecting scripts. So the sensible next step is to move the modifications from JavaScript to the C++ realm so that they cannot be inspected directly by an attacker and can only be observed through side effects. So they mentioned a project called Visible V8, which might be one option for researchers to control the replay of a website without changing the JavaScript. Yeah, some other countermeasures is that some anti-debugging techniques are difficult to bypass entirely. So the authors propose a need for a forensic browser with countermeasures that can enable debugging of client-side code to be reliable in the presence of malicious code. Yeah. The reason is that, for example, something like preventing the JavaScript code from learning that a breakpoint was hit is much harder, and it can only be handled by modifying the browser itself. So yeah, that's it.
Yeah,
the last,
okay.
Yeah, last part is related, but I think last part is related work. So I'll just skim through the headers. So this research is related to general anti-debugging on traditional malware, and as well as malicious JavaScript. But malicious JavaScript mostly focuses on drive-by attacks and discovering malicious websites.
Yeah, I think that's all very interesting.
Yeah.
I think both you and Yijie maybe look more into the detailed attack, because I think Docas focus more on the static malicious code, and Yijie look into more dynamic web page behaviors. And I think we need to discuss more. And I assume that we have the meetings on 4 p.m., right?
At 4:30.
4:30 p.m. Okay, so maybe I can make a brief comments on this work. I think this work is very interesting, but it is published on the top tier security venue, USENIX, and we know that the security big four is hard and usually only the top researchers can publish a lot of things, and usually in researchers, the more top tier conference paper you can publish, it somehow determine your status in the academia. So in this, I think for this work, one of the very good advantages that they just define, they conduct fairly extensive experiments, and they convey their insight. But one thing I feel a little bit disappointed at is that they convey less insight. So we know the phenomenon is what we're going to do. And is there a technique we can derive from these empirical studies? And what is more insights can we know that they're so largely above the invasive technique? But one thing we can conclude, but when we read a paper, we do not just want to read a paper. We want to know that whether the knowledge and the conclusion of the paper can serve our own research work. And maybe Yijie and Docas, you can think more in these directions. And for my point, I think we can look more into this perspective. Because Docas is the presenter, I just focus a little bit about the static analysis part. So when Docas looking into the phishing kits, right? Those phishing kits are usually the PHP, either PHP or JavaScript. So we look into this code, and we summarize, not only summarize the malicious intention, sometimes malicious intention need to be hidden under some more explicit benign code, whether we can have such observation. And then once we have such observation, whether there's a way for us to label those malicious intention. So once we accumulate a large amount of data, whether we can, at the beginning stage, we can manually label those code with malicious intention. But later, whether there's a way that we just divided the code into malicious code and the benign code, and then we learn the features automatically from those code, and we can form another very interesting topic there. And for EJS, I think one way we can try is that we can learn from this paper is that the malicious code always have a difference with benign code, and maybe malicious code will be more diverse. I don't know whether we can capture that. So when running a malicious code, and if it is contains an evasive technique, each time we run it from different locations with different browsers, it will show more diversity based on, because it will need to hide the contents, whether we can think in this direction to detect the malicious dynamic behaviors and intentions. Okay, thanks, Docas. So next one supposed to be Yuchen. Would you please share your slides? Oh, by the way, thanks, Docas. I think the preparation is really good.
Yep. Okay. So shall I begin?
Sure.
Okay. So today I'll be presenting this paper called "When Threats Meet Events: Efficient and Precise Static Race Detection with Origins." And this paper is presented at PLDI this year. The authors of the paper, there are two co-first authors. So the first one is Liu Pezhen, and she's a research assistant in the Texas A&M University. And her research interests are incremental analysis, pointer analysis, concurrent systems, program testing, and debugging about concurrency bugs. And secondly, we have Liu Peiming, and he is a first-year PhD student in the Texas A&M University. And his research interests are programming languages and static analysis. So other than that, we have Li Yanzhe, and he's a software engineer at Coderec, and he's also a first-year PhD at UBC. And similarly, his research interests are programming languages, program verification, and type theory. And we also have Prof. Cha Che-Cai, and he's an assistant professor at the Texas A&M University as well. And his research interests are on operating systems and runtimes, software system security, secure hardware virtualization, and cloud computing. Next, we have Prof. Dilma da Silva, and she's a professor at the Texas A&M University, and her research interests are cloud computing, operating systems, distributed computing, and high-end computing. And then lastly, we have Prof. Jeff Huang, who is actually the mentor for the first two authors. He's an associate professor at Texas A&M University, and his research interests are software engineering, programming languages, concurrency, and runtime verification. Okay, so let's get into the paper proper. The background and motivation behind this paper is to solve race detection in multi-threaded code. And I guess the prevailing environment right now is that the best techniques are based on dynamic analysis, but dynamic analysis has very high overhead. And on the other side, we have static analysis, which is mainly pointer analysis. But the problem with that is that it's difficult to scale because there's a lot of objects and there's a lot of things to keep in memory. And the paper also pointed out that we have two sort of paradigms to look at concurrent programs. There are event-based programs and there are thread-based programs. And sometimes the program use both kinds. So the paper mentioned that event-based traces are a bit more difficult to detect. And this is even harder when the events interact with the threads in distributed systems. Yep. So this paper basically comes out with, I guess, a variant of a context-sensitive pointer analysis. So instead of using the normal pointer analysis, they came up with an abstraction called the origins.
By the way, Yuchen, so I think this work is very technical oriented. So when you prepare slides, have you ever prepared something what is data race and what is point analysis? Have you prepared some introductions of these techniques?
Yeah,
okay,
not so
great.
much on data race, but I do have a few slides on the pointer analysis.
Okay.
Yeah, so the contribution is pointer analysis, right? And they also added some optimizations for race detection, but I think this one is less of the focus in this paper. They didn't really go super in depth in this part. Yeah. But okay, so let me introduce origins first. So the idea of an origin is to create this unified concurrency model in program analysis. And basically what an origin is just like an entry point to some fork in the execution path, I guess. Yeah, something like that. So formally it consists of a starting point and some attributes, which can be thread ID, event type, the parameters, or the used variables in that scope. So some examples we have like when we call thread.start or like a runnable.run. So
so they are still working on the Java core, right? So their implementation is based on Java.
They also have a C++
version
implementation. Yeah.
Okay.
Yeah, but most of the examples here are in Java. So yeah, so these are threads, and their past work is also mainly focusing on threads. But now they extended the support to events. And for events, we have something like the action performed on message event, handle event, stuff like that. Okay, so now pointer analysis. So if you remember from the previous presentation, which is quite long ago, pointer analysis is basically a way to denote what variables point to what objects. So a pointer analysis graph will contain pointer nodes and object nodes. So the object nodes will be the memory locations of the objects, and the pointer nodes will be just some reference. And from there, we also have a points to set, which is the set of object nodes that the pointer node may point to. So as an example, let's say that we have this sequence of code here, x equals to new t, and then y equals to new t. So in this case, we have a reference x, and then it is pointing to object O1 created by this new t. Now in the points to graph, or the pointer analysis graph, we would actually create an edge from O1 to y. And then for this second line here, we have O2 pointing to y. And then when we assign x to y, we point from x to y. Yeah, so this arrow here, the edge, actually represents a subset relationship between the points to set of the different references. So in other words, x here, the points to set in x contains O1, whereas the points to set in y contains O1 and O2. Yeah, so any questions so far?
So my comments is here is that so at some point there's when we are using analyze the code in a static way, we can always we were saying that the y can refer to O1 O02. But on some point, for example, after the execution of y equals x, and y can only be pointed by O1, right? So O2 will not be the choice.
Yep.
So in this case, so I forgot, my memory kind of fading there, but I assume that there have some more precise point analysis, because given the static analysis, we always have the completeness, but there's no less precision. So when I have the soundness of there's always a trade-off between the soundness and the completeness. So by the way, so Yuchen, I think, made a very, very good explanation on what is a pointer node and what is an object node. And also the relation is actually the point to set. So that is very important concept. And remember on those concepts, we can help us to understand the following explanation and introduction. Okay, so the key concept is here, we have the pointer nodes and we have object nodes. And all object nodes are always constant, right? And a pointer nodes, and there's they can switch and it will be changed later. And the relation is actually based on point to sets. That means there's more possibilities for one point nodes to different of the object nodes. Okay, let's keep going on.
Yeah. So Dr. Lin raised a very good point about the kind of flow insensitive nature of this pointer analysis. So what this paper actually does is basically to couple the reference nodes. Basically, just couples of all these nodes with the origin of the code. So this is a sample of the inductive definitions for creating our new pointer analysis graph. And yeah, essentially, this is the intra-origin constraints. So over here, right, we have like basically standard execution of code. So we don't talk about the new threads or new events yet. So in this case, yeah, we basically just follow the inductive rules to create new nodes when we see each statement. So here I have a question for the audience. So take, for example, this case where our points to set for y is ABC. So what edges will be created when we see this line here, xf equals to y?
It is simple. So anyone want to volunteer? So I think there is more about the probe analysis. So maybe I can talk more about why the probe analysis is important. So nowadays, I think more and more people are learning programs. So as I know that in the elementary school in China, and the Python languages are put into the textbook. That means in the future, more and more pupils or the secondary students will learn the programming. And we can foresee that more and more programmers will be created. For example, smart contract will be used as for tradings. And also there's stock tradings will be just conducted in a program. The socket tradings will be conducted in the programming programmatically, right? So in the future, they will have some human traders, but more and more junior traders will not be humans. It will be machines and robots. So in this case, how to infer the program code is very important. For example, we want to know what is the intention of the code, and whether the code has a bug, or whether the code actually will include some vulnerabilities for us to exploit. So those kind of techniques are emergent. That is old technique or classical technique. But with the emergence of more and more code and the programs that play a more important role in this society, and there have the emergence and the need for some probe analysis will be far more important than before. So in this case, we are looking to very basic concept of true analysis. And a point to analysis is a very, very basic technique for us to understand and analyze programs in a precise way. So the idea is that we have two variables in the programs, and maybe these two programs and these two variables actually refer to the same object, or in other words, they are referred to the content of the same memory. And once we want to do the analysis, if we see that the variable A, if variable A and variable B are point to the same object, if variable A can incur some bug, it means that variable B have the same property, right? So for now, Yuchen is just to give an example as to what is a point analysis. There are some object nodes, there are some point nodes, and there is the point to sets. So all these techniques or all these concepts are just serve to one goal. They want to know whether two variables actually point to the same memory allocation or the same object. Now come back to these questions here. And in table 2, it actually showing the rules, basically showing the rules and how do we infer the point to analysis relation. For example, when we are a new class and we assign the new object to X, we're saying that, and let me say that the left part is actually a statement, and the right part is a rule to infer how to parsing or how to build the variable object relations when we execute these statements. So for example, for the first statement, when we create a new object and assign to a new variable X, and in this case, we're just build a rule is there, and we have origin here and we have the X here. And then if the OI on O is actually a variable, right? So if O will actually have the set of the O on OI, and now this X will can point to OI as well. So based on these rules, and we can just go through the code and code statements on statement by statement, and finally build the object variable relations. Right. So now Yuchen, now let's come back to Yuchen's points or Yuchen's object. So assuming that Y actually here's Y basically, and Yuchen, you can just reframe a little bit here that. So this is a point to set, right? This is a point to set. That means Y, this variable Y actually corresponding to OI. Am I right?
So OI is the origin of this variable.
Okay.
Yeah, so actually you just take it as just some extra information that's together with Y.
In your point analysis, the Y point to another object node OI, right? So this is what do you mean, right? Okay.
No. Actually, the OI is for origins, so it's basically like a context.
Okay. So the point is that when we have a Y and then ABC are variable, right? ABC are variable.
Yeah. We can think of it. No, we just take it as an object. Sorry.
Oh, sorry. ABC are objects. So basically, it's better to be O1, O2, O3. So that'll be a better way, right? So
yes. Okay.
Yeah, I think Darren asked the same questions, whether ABC are variables or objects. So if they're objects, so there's O1, O2, and O3. And then when we have these rules, this is actually assignment rules here, right? And in this case, how can we link the objects back to the variables? So that is the question. So I think I have an explanation there. Anyone would like to volunteer to have a try?
Yeah. So Darren also raised a good question. Just to keep it simple, the origin is also OI.
Okay. So Darren, do you want to have a try?
I'll type out an attempt at the answer in the chat.
Okay.
Yeah, so basically we just point from Y to ABC, yeah, like you wrote. So the origins are the same. And basically now, I guess I sort of messed up the slide order a bit, but basically now instead of having each pointer node being just the reference, it becomes a tuple of the reference and the origin that it's in.
So origin actually means thread, right? Origin.
Yeah, basically it's a abstraction over thread, but also events. So it can be either threads or events.
Okay, yeah. So, but why do we need to distinguish the thread? And so you can think about it, if we run a Java program, the origin is independent from the object is independent from the thread, right?
The object is independent from the thread.
For example, we have two threads running in parallel, and the thread 1 create an object, and the thread 2 want to refer to the same object. So actually, this object actually will be installed in the JVM heap.
Yes.
So why we need to distinguish the origin? Never mind.
Yeah.
If you can address the questions, it's fine. If not, then let's just keep going. Yeah.
Actually, I feel that there's a bit of a case where, say that I create a new object within within two instances of the thread, then those two actually has no relation to each other. And I think that the reason why they added origin is to basically to differentiate these cases. So if it's a shared object, then if we look at the origin,
I agree with you. I agree with you. So the point is that the object created by different threads were definitely different objects, and they're actually talking about the state analysis. So if we just go through the code, how do we know that objects with the same symbol actually refers to different object, right?
Yeah. So this brings us to inter-origin constraints. So when we create a new thread or we register a new event, these will basically generate a new origin, and then all the new references and objects within that code block will now be paired with the new origin. Yep. So just as an example, so for example, when we create a new object, and we consider this as a new origin, right? Then the dispatch here, we will create a new origin OJ, and we pair it to the method in it. And then the new object in origin OJ will have a points to edge to the this within the constructor. And it also points to X, which is what we assigned it to. And then all the parameters passed to the constructor, B1 to N, points to the parameter name within the constructor, P1 to A.
Okay, so this is basically the proven semantics. So let's back to Darren's questions. So let's back to your questions, and Darren answered it in the chat. So can we go back to the question there? Yes. So here that when we assign y to exponent f, so here and here the questions and what to answer?
Yeah, the answer is correct. There's basically one edge for every object in the points to set, and it pairs with the same origin. So it's correct. Yeah.
Yeah, they have the same origin, and how about these 01, 02, 03 are actually will be associated with f, right? Not x.
Associated with f, not x.
So this supposed according to so it's supposed to using the third rule, right?
Yep.
The third rule, so we're pointing to f instead of the we're pointing to f. And how do we distinguish x here? Here I have a question here. So here it means that for for the third rule, it means that for every object has a point to set in the pointer set in X or Y, right? It will assign to this O is the okay. I got a point. So this O, that means O dot F here. I think a better way is that you still need to provide where these X, where those X are coming from, right? So that is the only way that we applied it. When you set up the questions, so you can see based on these rules, and based on these rules, we need to assign all the O in the pointer set X. So at least in the questions, you need to show on which objects are in the pointer set of X.
Oh yeah, I realized there's a mistake in the typing. It should be X.
You should provide both X and Y. You should because we need, so you can see in these rules we have X and we have Y, right? So that means we need to have all the X.OI and Y.YOI, so they're all related.
But actually, the points to set for Y would not be would not be, yeah, it's not needed in this induction. Because it's just a reference, right? So.
But Y will actually also have maybe 04, 05, right?
Yeah, so this 01, 2, 3 will be added to here, but in the graph itself, it won't point to 04 and 05.
Well, for example, we have X. Sorry, I take a little time longer here. So we have XOI equals 01 and 02, right? And we have YOI. Suppose we still have YOI here. Y1 I missed it. So we have, suppose we have, let me think about it. So XOI actually point to 01 and 02, right? And the Y, okay. So I'm not sure why my mark has been cleared. Can you see my mark there?
I can see it actually.
You can see it, but what I think when write a few, my stroke will be cleared from time to time. I don't know why. Okay. Thanks, Docas. So maybe we can skip these. My point is that if we want to finalize or concretize the third rules, we need the pointer set of both X and Y, right? And then there is supposed to be a combination.
Yes.
Right, we have combinations, and then we can assign the objects here. And in this paper, and I think one of the distinguishment, one aspect distinguish one another is that they allocate every X or every object with an origin, right?
Every object with an origin. Yep.
Yeah, that is the major. So they redefine all the operation semantics here, and it makes the operation semantics a little bit more complicated. Okay, let's keep going on. I hope that I make myself clear, and I hope that this talk can also keep attraction for the audience. Let's keep going on. Yeah.
Okay, so objects assigned. Okay, so these are basically when we create a new thread and we run it. So yeah, we went through that already. Okay, so I guess we can show you, I can show like an example of the call graph. So this is, the paper did not provide any like pointer analysis representation, but I think it's good to just maybe look at the call graph here. So I think I didn't mention it back here also, but when we are creating this, we also create a call graph. So basically just what methods lead to what other methods. And so in this code snippet here, we have one object, O1, and then we create these two operations, which are like threads, right? So we run these two threads, and then within the two threads, we actually create a new object. So by right, these two objects are separate and they are local to their own threads only. And what it would look like is basically something like this. So O6, we pair with T1, and then this just means that this local to origin T1. And for T2, it's local to origin T2. And if we try to access S, then this S is in the origin of T main. So we can see that it's accessed by both T1 and T2. And the call graph that is being created will look like this. Right, so our main method foo will run the constructor for T, and it will also run the run function of the thread. And these two are separate as annotated by the different origins. Yeah.
And yeah, so I have a small question here. So here we know that for example, 06, the origin of 06 is T1, right? So when we're passing 06 as the parameters to create another thread, and how do we annotate the origins of 06? Suppose 06 is used by all the code in the new origin. Have I made myself clear? So when we have created a new object, for example, 06, and 06 will serve as the parameters to create another origin, maybe big O5 or big O1. And when all the code, and how do we how do we process do we need to change the origin of 06? Yes.
Let me think. I think that we create this new, so the object origin is still
still O1, right? Suppose origin.
Yeah, it's still O1, and then the reference one will be the new OI. Yeah.
Okay, let's keep going on. Yeah, I hope this talk will be not so boring. Yeah.
Yeah, it's a bit involved. Okay, so lastly, we have the origin sharing analysis. So basically, we just track whether the object access in the code path, whether where their origin is, and whether they are accessed by from more than one origin. And if at least one of them is a write, we mark this access as origin shared. So I think the algorithm is quite straightforward, so I didn't make more slides on this. But basically, we start off with the method, and for each statement of our read and write accesses, we just find the origins of that reference. We find the origins of that reference, and then we just see whether there is sharing or not. And it is just like the paper stated. So,
so I mean to ask the rationale of the original sharing analysis. So why two objects will share the origin? And you can see that how do we define the origin? The origin actually is the thread or event creating that object, right? And then the object will just be used everywhere. And why there's a need for an object to be sharing? Because just like parents, the origin seems more to me like a parent. So a parent create children, give a life to children. Even if the children is adopted by the other parents, there's only one origin who give the life of the children. Or there's only one origins. And it seems to me that 1 year we can only have one origin. And whatever it passed somewhere else, it will just have one origin. Is my understanding correct, or is there any use for that?
I think you are correct so far, but I just feel that okay, let me think of how to phrase it. They are not checking whether the object itself like has overlapping origins. It's more of the access, and I think the access in this case just is defined by the statement at which this access is happening and the field being accessed. So these two is a reference, and then the reference will point to a lot of different objects, and then those objects might have different origins.
So let me repeat. That means that the origin is not, so the relation between an object and an origin is not mean that origin create an object. Is that at the current moment or at the moment, and what is and whether the origins, whether it can be accessed by multiple origins. And origin is more like context. It verify whether it is legitimate to visit this object. Am I right?
Yeah, I think
Yeah,
so.
for example, it will create, for example, some thread create an object. So the audio variables in this thread has a right to access this object. But when we passing this object into some other threads, that means passing this to another origin, and this object begin to have two origins. It means that the variables in both threads or both origins has the legitimacy to access this object.
I'm not sure. I think that makes sense. I'm not sure if the analogy is the same. My understanding is that there is we have different references, right? And then the references has their origin, and then we point them to maybe other references which might have other origins, but the final object that we point to has the fixed origin. Okay.
Yeah, so but the origin is not about variable, right? The origin is attached with an object.
Yeah, when they get the origin, it will be the object one. Yeah.
So what is analogy here? So when the variable, so what do you mean by each circle? Each circle is an, and for example, what is your circle and the rectangle means in your drawing?
So this one is the reference, and then this one is the object.
Okay, the reference means the variable.
Yeah, reference the variable.
The reference and basically the reference is just a reference an object, and the reference itself does not have origin. And what is domain model and mental model we are discussing here? So does a variable have an origin?
Yes, I think the variable has an origin.
And an object also has an origin.
Yeah, but actually, yeah, now that I think of it, then the variable's origin is not really useful anymore, right?
Yes.
Yeah,
So we have discussed for I think quite a long time, 5 to 10 minutes here. So what I'm trying to clarify or make it clear is that, you know, what's the rationale of this original sharing analysis? Why two objects? So whether and what is the subject to share the origins, variable and object? If it is variable, either variable or origin or object, why do they need to share the origins? And what these shared origins can bring us, and what benefits can we have if we let multiple variables or origin to a variable and object to share the origins, and which we need to make those points very clear.
variables and origin sharing.
Yeah, what's the point to let them share in origin?
No, I think the sharing is basically like, let's say that I have I'm reading from variable R, and then all the objects that I might point to, their origins are J and K, for example, right? And then later on, I'm trying to write to another reference variable, and then this reference variable might also point to here. And then the shared origin will be.
Yeah. So why they need to share it? So so you can think
I
about.
think
So let me write.
when you're
Let me write something down here. So let's make things very simple here. So can you see what I'm drawing? So
Yeah.
suppose we have a y variable, right? It has an object O1. Let me write O1 means object 1 means object and have original 1, and object 2 have original 2, right? And also object 1 may have original, object 3 have original 1 and origin 2. Whatever it is, I just make it up. And once we have assigned y equals x, x equals y, and here x will have already point to assess maybe the original 4 and 05 and object 4 and 05. Okay, so we just take a union of these two sets, right? Is that true? And here, so now it doesn't touch any origin part. The origin are just simple there. And in what case we need to share this origin? Share the origins means that these origins will be serve multiple object, or one object need to serve multiple origin. So the former or the latter?
The object serve multiple origin, or the origin serve multiple object.
Yeah.
It should be the latter. I feel like the case here is just that when there are references like this, and then the objects that they might point to overlap. I think that's all that this code is trying to find.
Okay, so the point is that, so suppose we have another, that means after assignment, if we have the original sharings, one object can have multiple origin. Am I right?
One object can have multiple origin.
So that's why we need to share the origin. Or one origin will have multiple variable.
I think it's the origin have multiple variable. Yes.
Okay, the origin has multiple variables. So, but origin is actually a context, right? So so suppose we have object still O1, right? These O1 actually have object 1. It have origin of O5. And after assignment, it means that this object 1 will have multiple origin. So all the origin, I don't know. So the point is that I still have confusion here. So the point is, what's the benefits here?
I think I have to go read the paper a bit more deeply, because actually this is basically what the paper said about the origin sharing. And I feel that the main case is just to figure out if there is a race, actually. I feel that this generates the pairs to the conflicting pairs, basically. And then from this set, they do the analysis.
The point analysis is someone to address the data racing. So the data racing is saying that if a variable, if two threads there, if one variable is returns, and at the same time, the same variable is returned by another thread. For example, suppose we have variable v, right? This variable v's, and in one thread variable is returned, and another thread variable is returned. Or in one thread the variable is read, and in another thread the variable is returned. If these two events can happen in parallel, then they are the data race problem, right? Think about it. This is about concurrency. So now the point is that we want to know that this variable v should be the same as exactly the same as this variable. These two variables supposed to point to the same variable, right? And then we call our analysis. So the point of analysis, from my point of view, is to address this problem. If we can re-identify to know that the identity of the two variables are actually the same, means that they point to the same memory or point to the same object, then we can allow us to analyze the data race problem. So it's just still a static analysis. Yeah, but my point is that why the origin need to be shared, and there are some benefits to, or there's a contribution of the shared or the shared origin to know that the identity of two variables are actually the same, right?
Yeah.
Okay, maybe we have. I think we already have a very long discussion here. Let's keep going on.
Yeah. Okay. So after we have the sharing analysis, we also have the happens before graph. So we use the origin pointer analysis to generate this graph. All right. So just to give some background about what a happens before graph is. So for example, let's say that we have the main method here, and then we create this new thread, and then we do some computation here, and then this thread does some computation here, and then this is joined. So essentially what happens is that we have a graph like this, and this is the .run node. And then this splits off to this line, this statement. And then afterwards, it's being joined. So basically, what I'm trying to say is that we create a representation of the execution of the program. And then we use these edges to determine if a statement happens before another. So in this case, we don't know whether this line or this line is going to be run, and therefore we cannot make like a ordering between these two nodes.
So that's very clear. Okay.
Yep. So this is what the happens before relationship is, and then on the right here is how the origin analysis fits in with the happens before graph. So for each statement, there will be write or read nodes. And when we call a function, we will also create a new edge from the calling to the first statement in the method itself. And then once this method is done, so there will be another edge from this done node to the next line in the caller method. Yeah. And then in the case where there's locks, we will have this lock and unlock nodes. And so all this will help us determine which event happens before another.
And by the way, so my follow-up question that is, and how the origin has been changed during the rules here. So so if x.f equals y, and then if we write, that means we'll create a write event, or so how do we interpret this one?
Yep, that's right. So we have a write event, and then this write event is acting on o.f in the origin OK. So yeah, so we have like a method. So we have the method m, and then this origin.
And what is role y place? Okay.
Sorry?
So the y does not matter, right?
The y, yeah, the y does not matter because it's an assignment. Yep. Yep. So
so in this case, what does dispatch means?
Dispatch is the resolution of the method. So for example, let's say that we do this run, right? But this is an overloaded method. So what it resolves to is the result of dispatch. Yeah. So
can we know which y on which f does it cause? Y.f, f is an interface or
F is the method name.
method, f is a method name. Okay. Okay, so basically it's telling that, so it will have the conservative analysis. So it will find all the f with such a name and build such a connection between them.
Yep.
Okay, so here we do not need to change the origin, right? So is there somewhere we need to change the origin? No need.
Yes. All the inter-origin rules. So when we join and when we do entry, so this entry would refer to like probably run and start, things like that.
So in this case, we will change or add the origin to add a new origin there.
Yep. So we'll create this new origin OJ.
Okay, so I think my interpretation may be correct. So the origin actually means the tokens or the legitimacy tokens. Only the assignment happening, only the assignment happening within these with the same origins will be allowed. Right. Maybe let's keep going on. Let's keep going on here. Yeah.
Yeah, I have to think about it also. Okay, so race detection basically checks each pair of conflicting accessors, and then we just run a search whether this there's a reachability. We do a reachability check whether these two nodes have happened before relation. And then if they do not, we need to check if they are protected by some locks. And that's basically it. So if they do not have the locks, they are reported as a data race. Yeah, so this is actually my own question for the paper, because I felt that the OSA is what was generating the conflicting accesses. So when some origin is quote unquote shared, then this access is the problematic one. So, and that's where they start doing the checks. Yeah, but I'm not fully sure also after, yeah.
Yeah, maybe we can skip this question. Let's keep going on. Yeah, so my point is that I think the ultimate, because you just provide a few the overall ideas, but I think if I'm the one who present the papers, I hope that I will just showing that what these origins, what these origins means, and what role can the origin play, and why this paper can improve the state of art based on the origin design. Right, and all those points need to be very, very clear so that we can understand the whole story. So usually when we look into a research work, it usually is not created from scratch. It must be based on some work happening before. So before this work is published in this year, PRDI, right? And before that, there has already been some data race problems. And what is the benefits and what problems of the existing data race detection problem cannot be addressed, and what's the benefits, and how origin can fit in and solve the existing problems. So we basically want to understand this point. Let's keep going on. Yeah.
Okay. So other than that, there are some optimizations that they made in order to speed up the calculation of race, to speed up their race detection. So firstly is that the happen before nodes are simply assigned a monotonically increasing ID. So instead of like an actual node from a write to read, for example.
There's all the rules or tricks or heuristics to make the calculation more efficient, so that we do not need to check the calculations back and forth, and keeping that information. Let's keep going on. Yeah. So I think that will be, in terms of the research point of view, that is a minor of course, that is something a plus. That is a plus, but these optimizations may not be fundamental.
Yeah. So basically, these are just some software engineering things that they did, and then they cache some of the queries also. So they
Let's skip this one.
Yeah, could speed it.
Through the experiment part.
Okay, sure. So they basically compared against other race detection algorithms, and they also and their baseline is the context insensitive pointer analysis. So this is the same algorithm that they use for D4, their previous work. Yeah, and in general, it's much faster than the other race detection algorithms, but it's slightly slower than the baseline. So we can see from this side of the table, the slowdown or speed up is given in the red font, and then it's in relation to the baseline. So we can see that there's some speed up in some cases, but a lot of the times there is a slowdown, but it's still a lot better than the other existing race detection algorithms, which is the KFA and
so
K object.
so my suggestion here. So I think this paper is interesting, and you know that PRDI is actually a top tier programming language conference, and maybe 2 or 3 PRDI paper, also with 2 or 3 PRDI papers can already establish him or herself in academia cycle. So this work supposed to be sufficiently strong. And also there are some professor like Jeff Huang is actually a tenured associate professors in UT Dallas. So I assume that in terms of paper presentations, we need to have some fundamental understanding why the efficiency can improve based on the context insensitive analysis approach. And usually when we conduct the program analysis, there's always a trade-off between the precision and recall, the soundness and completeness. That means the more accurate the results, the less complete a small case we may miss, and vice versa. And the state-of-the-art work is always push the trade-off into a new boundary. That means we sacrifice less soundness, but gain more completeness, or vice versa, right? Only achieve this point, and can we have a new achievement? So my suggestion that for the paper presentations, and if you can just review the paper to see how they make the trade-off, and in terms of precision and recall, and which one they sacrifice, and which one where they have more gains. We need to have such understandings. Otherwise, the time of reading paper may pay in value.
Okay. Yeah. So other than that, the precision is a lot better as compared to the CFA methods, and on average, there's a 77% warning reduction.
Okay.
Yeah.
So that's great. So that's the results, but I think we need to focus on more of the rationale of their design. Yeah. Okay. Thanks, Yuchen. So if you can revisit the papers and find more insights, and maybe we can have more discussions in our next individual meeting.
Yeah.
Okay. Thanks, Yuchen, and thanks everyone for lasting until now. I know that a lot of you are not the expertise in program analysis, and then maybe it is also not a research interest. But anyway, sometimes it is also good to broaden your expertise. Maybe someday you need it. Okay, thanks everyone. And then, by the way, is there any questions? Okay, if there are no questions, let's call it a day. Bye everyone.